As you know, one of the long-term themes in our course has been intellectual history and the impact of epidemic diseases on that. And this morning, in that light, I'm going to be looking at one of the great medical debates, in particular, a great medical debate of the 19th century, which was the so-called debate between Contagionism and Anticontagionism. Now, why would we be interested in it? First of all, if we're going to understand 19th century medicine, we have to realize that if you were to go back, say, to reading The Lancet, one of the major medical journals of the 19th century, or say the proceedings of the French Academy of Medicine, you would see that they were one of the leading issues that was being hotly debated was the rights and wrongs, the scientific evidence for and against the idea of contagionism, and its opponents, the idea of anticontagionism. So this was really a hot-button topic in 19th century medicine. It consumed the middle decades of the century. So if part of our course is to understand what was happening in the world of medicine, well, this debate was really crucial in it. Another part of our interest in this debate is that it brings to a conclusion much of our consideration of Asiatic cholera. We've talked about the impact of cholera, and we need to recognize that its impact was partly in the realm of ideas. Its legacy didn't include just death, fear, social tension. It didn't just leave behind it sewer lines and water pipes in Britain, the broad boulevards of Paris and Lyon, the rebuilt lower city of Naples. In addition, it left behind it a major debate on the causes of disease and epidemic diseases in particular. And this is the debate between contagionism and anticontagionism. It's useful for us to turn to this debate also because it helps us to prepare the ground for one of the most important discoveries in the history of science, and certainly medical science, and that's the establishment of the germ theory of disease, which is our topic for next week. So what we'll want to do then is we'll be moving towards the victory of contagionism. So this is a debate then that really mattered in medical history. Now, in discussing this issue, there are a couple of pitfalls that I think we ought to avoid. They're distorting and make it difficult for us really to understand history in general and history of science in particular. Let me point out two pitfalls. The first is a possibility of what's been called the Whiggish view of history. Now, in its application to science, it sees history of science as a linear upward march of truth, moving steadily forward over ignorance and obscurantism. That is, a history of constant progress. And it's reinforced if our history of science deals and examines exclusively the ideas that finally triumph, so that we study only a constant progress, the march from one great idea to the next. Another possible danger and pitfall is what's called presentism, which I might define as the rather smug view that science all along has been striving, almost in Lamarckian manner, to make the benighted people of the past finally emerge as smart as we are. And we get to look back condescendingly on the thinkers of past centuries, giving them marks for how right or how wrong we now know that they were. So to avoid those pitfalls, What I'd like to do is to approach this in a different spirit. Next time I will take the more traditional path of looking at the victorious germ theory of disease. And at that point, we'll pay our respects to the famous trio of 19th century science that you all know of: Louis Pasteur, Robert Koch, Joseph Lister. And in doing that, we'll notice that what triumphed wasn't only disembodied scientific truth. I'm not disputing, let me stress this, I'm not going to be disputing the truth of the germ theory of disease, but what I want to do is something a little more subtle, which is to notice that what triumphed wasn't just disembodied truth, but also a worldview. And that when that worldview won out, there were some losses as well that went with it. The germ theory of disease is one of the greatest advances in the history of science. But we need to argue that although true, it perhaps wasn't the entirety of truth, and that its establishment as a reigning orthodoxy by the end of the 19th century, because it does, in fact, come to be held by the entirety of the international medical community, really after around the 1890s or so. And that brought with it one of its consequences, an unintended one, was certain negative impacts on understanding of disease that we'll be talking about. And to understand and appreciate this fact, I'm going to concentrate this morning not on the victors. You know about them already to some extent, and we'll be turning to them for the whole of next week. But I'd like to look instead at someone you probably don't know, or maybe not know at all. In fact, just out of curiosity, had before we talked about him in our course and reading, how many of you had actually heard of Max von Pettenkofer? See, that's what I suspected. Actually, no one had heard of Max von Pettenkofer. So all the more reason the good news for you is we're going to be dealing with him for the next 40 minutes or so. He's the most sophisticated and scientifically robust of those who were, as we might call, wrong. He lived from 1818 to 1901, and one of the great figures of 19th century medical science. Although his scientific defeat was total and humiliating by the 1890s, and indeed that might form part of the background to the fact that he was to commit suicide at the turn of the 20th century when he shot himself. But I'm going to try to understand that he was not just simply wrong, but I'll argue that he was splendidly wrong. That his mistaken ideas actually saved millions of lives, and that their defeat had a paradoxical consequence, not only of advancing medical science, but in some ways impoverishing it in ways that are important and that we might want to consider. Well, who was Max von Pettenkofer? And since you hadn't met him before, let me introduce you to him. And here he is in splendor. And he was a German scientist and physician. In particular, map of Germany. Pettenkofer is associated with Bavaria here in the south of Germany. Let's look at that a little more closely. And he was associated especially with the city of Munich. And I'm pointing this out to you not simply so that you'll know where he's from, although that's nice to know, but this is extremely significant in his theories, and that he tends to be the defender of localism and the autonomy of Bavaria and Munich against the centralizing tendencies of Germany as a whole. So it has a political significance that we'll be turning to. Now, what were his social origins? Who was he? He came from a Catholic family of very modest means, but lots of children. And the family, that is his nuclear family, didn't really have the means to afford him with a higher education, and he gained that because of an uncle. He had a wealthier uncle who was a prominent apothecary, but alas had no sons, and he wanted his nephew Max to carry on the family business. So Max von Pettenkofer started out life by studying pharmacy and chemistry, and this, in fact, was to have an impact on his medical theories. But he soon discovered that he hated the subjects he had originally enrolled in to study, and he terminally disappointed his uncle when he enrolled in as a medical student. And he gained his medical degree in 1843 from the University of Munich. Thereafter, he had a varied career for a few years, casting about for what he wanted to do in life. He worked for a while for a mint, and he even had a failed attempt to become a stage actor. But in 1847, he gained appointment to the medical faculty at Munich and became also a professor of organic chemistry. From then on, he enjoyed a meteoric career as one of the rising stars of science in Bavaria, in Germany, and Europe in general. He became advisor to the Bavarian government and a full professor of medicine in 1853. Now, 1854 changed his life, and it did so in relationship to an outbreak of Asiatic cholera in Germany. And it's interesting that this is the very same epidemic that Snow studied in London. But whereas Snow was a contagionist, Pettenkofer reached the exact opposite conclusion. Indeed, thereafter he became a lifelong opponent of Snow's ideas and what he referred to with scorn as the English water mania. The English, he said, were obsessed with water. Well, what was the debate, and why was it so passionately held? Now, the debate was obviously about the issue of whether diseases are contagious or not, but it didn't involve all disease. No one doubted in the 19th century that syphilis, for example, was contagious. The debate was about a subset of diseases, 5 in particular: leprosy, typhus, and then what we might call the big 3: plague, yellow fever, and cholera. In other words, the debate centered on the diseases that were the most feared diseases of the 19th century. And so the debate was passionate because it concerned diseases that were extremely important, and it wasn't just a matter of academic disagreement. The decision on whether you defined a disease as contagious or not had a practical importance. It meant what are going to be the public health strategies that you devise to combat it. And the European powers were greatly divided as to whether they should defend themselves by quarantine, the great anti-contagionist measure, or not. Well, the two sides in the debate then were contagionism and anti-contagionism. Let's start with contagionism. This wasn't a new idea at all in the 19th century, but it was unknown to the Greeks, but it was part of biblical tradition, and you've heard of its popularization already by the Italian physician Fracastoro in the 16th century. Contagionism had a widespread importance in popular culture as well. The contagionist idea by the 19th century was that there was some infectious material. Some people thought it was a poison, a chemical in other words. Others that it was pure speculation, a living entity, an animalcule. You'll see that word in John Snow, for example. in one of his speculative moments, that was transmitted in some manner, perhaps person to person, perhaps through the pores, perhaps by contact with a sick person, perhaps by objects that had been in contact with that person. And you've just been reading a very powerful expression of the contagionist position, and that's the work of John Snow. But an important thing to remember was that down to the 1890s, contagionism, and this may surprise you, was primarily the standpoint of popular culture rather than of the medical elite. Whereas anticontagionism dominated the international medical profession. Most men of science regarded contagionism as a view held by the ignorant and the superstitious. And indeed, the irony is that contagionism reached a nadir in respectability just before the work of Koch and Pasteur demonstrated its ultimate vitality. To understand that, take an example that by now you know extremely well, and that is plague. To the layman, the spread of plague seemed to justify the idea that by some means that people still didn't understand, it spread from one person to another. But to the learned physician, the case for contagion still seemed weak. There wasn't a mechanism to explain what it was, how it was transmitted. In many cases, close inspection seemed to demonstrate that the disease spread without the direct contact that the contagionist view seemed to postulate. People caught the plague who hadn't been in immediate contact with another plague victim. Conversely, where there was such contact, often the plague didn't spread, and people who cared for a plague victim sometimes didn't fall ill. How could that be explained? Furthermore, epidemics of plague began and ended in the most mysterious manner that no one could plausibly explain. And to strengthen their case, the contagionists would need to discard their theory of inanimate contagion, replacing it with something that was living. Furthermore, there was the need for the idea of transmission over distance, by water perhaps, food supplies, or later we'll see insect vectors. But the debate was also fueled by political conclusions, by politics, because major conclusions followed from the position that one adopted. Contagionists, in their scientific conclusions, were people who buttressed the power of the state. Because in the name of state power, one could institute the most draconian measures: cordons, lazarettos, quarantine. You could sequester, and confine individuals. You could limit civil liberty, and you could radically control the movement of goods and of trade. So one of the results then of contagionism, you can see here, the idea, here you have cholera, yellow fever, and plague trying to enter the citadel at the gates. And here we have quarantine and the draconian measures that follow from that. Cleanliness, you know the filth, by now you're experts on the filth theory of disease and the measures to be adopted against it. So the idea of contagionism buttressed those ideas of a strong, powerful state interventionism. Now, let's turn then to their opponents, the anti-contagionists, the people who were skeptical with regard to the ideas of John Snow. These were largely associated with the political left. Why? Anti-contagionism implied free trade, it was associated with liberalism and with the defense of individual liberties against arbitrary state bureaucracies. It implied opposition to extreme and sometimes violent plague measures of public health. So it wasn't by incidence that it was a good idea to look at a map of Germany, because the most important of the contagionists, Robert Koch, was an icon and promoter of the power of the centralized German state. He worked in Berlin, and that wasn't by chance. And he defended the centralizing and imperial interests of the German Reich. Whereas Pettenkofer was a liberal who championed the local interests of Bavaria and Munich. And indeed, his theories coincided both medically and politically. They were sometimes referred to as localism. Another way of seeing the stakes in this debate is to remember that Britain long opposed the contagionist position. There were in part for political and economic reasons. That is to say, Britain was ranged in the international conferences largely with anti-contagionists, in part because its interests prospered best through free trade. And it felt threatened by medical arguments that implied that the state should interfere with commerce, impounding British ships and quarantining their crews for 40 days. The anti-contagionists also had the imprimatur, should we like, of tradition, of the authority of tradition. Their views were sanctioned by Hippocrates and Galen, and were buttressed by a whole panoply of ideas that had grown up later, but were, if we like, compatible with the traditional practice of medicine, with the idea of atmospheric influences, of the epidemic constitution, as it was called, a bit of jargon for you, of the atmosphere. And it was compatible with the filth and Mayat theory. Let's also remember that anti-contagionism inspired some robust health measures as well, and it saved lives. Anti-contagionism was the view of people like Chadwick, whom you know now, and his associate Southwood Smith. It was the view of Osman and the Second Empire, and it was the official doctrine of risanamento, that is, the rebuilding of Naples. Now, in the history of medicine and public health and epidemiology, the cholera epidemic of 1854 looms large, giving rise to two foundational texts of epidemiology on opposite sides of the debate. On the one side, we see John Snow, and you've read his On the Mode of Communication of Cholera, the final version of which it was first drafted in 1849, but the draft that you have appeared after this event. And this was the classic statement of the contagionist view, to the extent that it could be supported without the definitive evidence later provided by microscopy. So Snow did everything that it was possible to do purely on the basis of epidemiological evidence. There was going to need to be a conceptual shift in order to clinch his view and demonstrate it so that it was broadly accepted. On the other side, we see a book that's been, it's not even on our own reading list, a book that's been largely forgotten. This is Max von Pettenkofer's work called Investigations and Observations on the Method of Spread of Cholera, published in 1855. And this, I should say, that Pettenkofer was no less rigorous as an epidemiologist than John Snow. And this was a major foundational text in epidemiology. It was a study of the 1854 epidemic in Bavaria, reaching conclusions that were diametrically opposed to those of Snow's. So from 1854, cholera became a lifelong preoccupation of Max von Pettenkofer, and he devoted himself to the epidemiological study of the disease, staking his reputation on high-profile debates with Robert Koch. He was to write some 200 articles and books during his lifetime on a whole range of scientific topics, but the largest number, about 60, were devoted to cholera and its transmission and cause. So Pettenkofer, and the reason we're dealing with him now, is he was the last major and the best defender of the anticontagionist doctrine, of miasmatism, in other words, and he defended it until his death at the dawn of the 20th century. He adopted the traditional doctrine dating back to antiquity, but provided it with a new evidence-based scientific underpinning. Well, why was Pettenkofer not convinced by Snow when it came to cholera? Part of the reason you know. Contagionism, Pettenkofer said, and in this he was right. It didn't produce a really plausible mechanism for the transmission of the disease. It correlated cholera cases with drinking water, but to Pettenkofer there seemed no means of explaining exactly what was transmitted or how. Also, as you know, Pettenkofer had been trained as a chemist, and he looked at the traditional idea that the cholera poison was some sort of chemical substance, and he argued that it was entirely improbable that a disease could be spread then in the manner postulated. Looking at London and the River Thames, how could a poison contaminating the Thames, if it was a chemical, not be infinitely diluted? Furthermore, he said there was a whole series of what we might call cholera mysteries that Snow's position didn't help to illuminate. Why did an epidemic start? And why did it end? Why could doctors provide their services in the midst of an epidemic of cholera and yet not fall ill of it themselves? What caused the pronounced seasonality of cholera? Why was its onset almost invariably in the spring and the summer? And why did an outbreak always seem to ebb with the onset of cold weather? And then, lastly, for the moment, there was what we might call the problem of Lyon, that is, the great second city of France. If cholera is contagious, and if it follows the great routes of trade and population movement, why is it that there are, nonetheless, major centers that escaped throughout the 19th century? Lyon was the second largest city in France, located at the hub of a network of trade and transportation. And it had it was a great textile center of manufacturing. And it had all the urban problems of an industrial center at its time. If ever, Pettenkofer would say, there was a city that seemed primed to be devastated by Asiatic cholera, it was Lyon, and yet it escaped the visitations of this exotic Asiatic outsider. Well, what was Pettenkofer's theory? And it was his delight to believe that he could provide an apparently clear, epidemiologically based explanation for all of those cholera mysteries. Indeed, another aspect of his theory, that Robert Koch discovered the Vibrio cholerae. You've seen a picture of the Vibrio. And he discovered it in 1883. Pettenkofer didn't reject the idea of the Vibrio. Instead, he incorporated it elegantly into his larger theory, explaining that it played a role in the etiology of cholera, but that its role and its mechanism were completely different from the ones that Koch espoused. Pettenkofer's theory is often referred to as the groundwater theory. We've seen it can be called localism. It can be called the groundwater theory. The simplest approach to his method is a very simple mathematical equation that he was very fond of himself for illustrative purposes. It was perhaps the simple of all mathematical formulas, x plus y equals z. What did that mean to Max von Pettenkofer? Well, for him, z was a cholera outbreak, the result, then, of combining x and y. It's produced, in other words, under certain specific conditions of two other factors, the x factor and the y factor. The x factor, he said, was the presence of the Vibrio cholerae. You see, he accepts that the Vibrio plays a role. But for Pettenkofer, the Vibrio itself, on its own, would never make you sick. You could swallow it quite safely and remain entirely healthy. He regarded it as harmless on its own, and as we'll see in a moment, he carried out a famous auto experiment in which he tried to demonstrate conclusively the truth of his view. In other words, he made himself a cocktail of the Vibrio cholerae and drank it. And in fact, he remained healthy and therefore persuaded to the end of his life that the Vibrio on its own was harmless. He was to say that the Vibrio causes disease in an entirely different but orthodox miasmatic manner. The danger doesn't arise when the Vibrio contaminates food and drinking water. The problem is different. It happens when the Vibrio gets into the soil beneath a major city. And there, Pettenkofer used a horticultural analogy referring to germination or fermentation. After the Vibrio gained access to the soil under certain conditions, it could germinate like a plant and give off its poison into the air above that the population inhaled. And those who were susceptible fell ill in large numbers, and it was then that you'd have the onset of an epidemic. So in 19th century medical parlance, cholera was an example of a whole category of diseases that were called zymotic diseases, diseases caused by fermentation. So that we see the X factor involves the Vibrio cholerae. Then the Y factor was simply those local conditions, again localism, that were necessary for fermentation to take place and for poison to be given off into the atmosphere. So what makes up the Y factor? So again, let's think of horticulture and the growth of a plant. A plant doesn't need only soil to develop, it also needs nutrients and fertilizer. And here was the critical role of filth and excrement. They were, in Pettenkofer's mind, the nutrients for this plant, the Vibrio cholerae. So unsanitary urban conditions literally fed the Vibrio. Sewage was dangerous not because it got into the water, but because it seeped into the soil beneath the city, nourishing the Vibrio and giving rise to fermentation. But there's more to it in Pettenkofer's epidemiology. Like a plant, fermentation required a number of other preconditions. It needed water. Plants always need water. It needed a warm temperature. It needed air and porous soil in which to grow. And it was at this point that we see why Pettenkofer's theory is sometimes called the groundwater theory. Groundwater was important to his analysis because he considered variations in the water table beneath the city to be a measure of the capacity of the soil beneath the city to support fermentation and give rise to cholera epidemics. Too high a water table would be like flooding, and that would kill the plant. Too low a table would be like a drought or a desert. So for a cholera epidemic, the ideal was an ebbing water table that left moist, porous soil above it, a condition that was likely to be characteristic of the early summer, and indeed, Pettenkofer now thought he understood the seasonality of cholera. He could explain its seasonality by reference to the water table of European and other cities. So armed with this theory, Pettenkofer proceeded to conduct exhaustive epidemiological studies of the local conditions of localities vulnerable to cholera. For Pettenkofer, it seemed obvious why mountainous areas, the Alps for example, weren't afflicted with cholera. There was such a deep layer of insulation between the groundwater and the population, who were therefore protected from the cholera poison. Similarly, desert areas provided no conditions for fermentation. Pettenkofer also thought that he had solved the Lyon problem. By investigating and studying Lyon, he realized that it was built on a thick layer of impenetrable granite. It was built on stone and therefore provided no opportunity for fermentation and germination. The best conditions were provided by cities that were built at sea level on alluvial porous soil. This could explain why Naples was ravaged, Paris, London, Calcutta. And then he decided, being an honest scientist, that he should also investigate in particular the hard case, the one that seemed to conflict with his theories, and that was the island of Malta. Malta was built on rock, but it experienced disaster during recurring cholera pandemics. And he thought to his own satisfaction that he could solve the riddle. Malta, unlike Lyon, was not built on impermeable granite. It had everything to do with the specifics of the stone itself. Malta was built on porous, soft limestone, and that provided infinite air-filled cavities that, if watered and fertilized in warm conditions, would provide wonderful places for germination. You can see Pettenkofer visiting Malta, which he did, and having his eureka moment. He did core samples. I'm trying to say that Pettenkofer was a very conscientious research scientist and a strong epidemiologist. And he went further. He argued also that he could explain not only which cities were most afflicted by cholera, but also the very neighborhoods within them. Low-lying areas close to the water table would be vulnerable to cholera. Neighborhoods built on hills would be protected. Naples was a good example. The lower city was ravaged, the upper city was not, and Pettenkofer thought he knew why. Neapolitans, as you know, in fact agreed with him, and Pettenkofer's theories were much admired there. It seemed to explain Neapolitan history, and it was his theories that were the very basis for the rebuilding project. So he saw his great achievement of that of developing a single unified theory with no internal contradictions that could explain all of the known facts of cholera and clarify those puzzling cholera mysteries. Now, an interesting point about Pettenkofer's theories. They're now rejected by modern science. But during the 19th century, they provided a major impetus to undertake needed sanitary reform. His ideas, therefore, can be credited probably with saving hundreds of thousands of lives from a variety of diarrheal illnesses. Cholera, of course, but also typhoid, gastroenteritis. So this is a case of an idea that we now know not to be robust scientifically, that nevertheless produced very practical results that had a major impact on combating epidemic diseases. Pettenkofer was responsible, in fact, for bringing the sanitary idea to Bavaria. He wanted to install sewer systems to take away waste and fecal matter, but not for the reason that snow would have. He wasn't worried that Bavarians would drink infected water or eat contaminated food. He was afraid that the fecal matter would get beneath the city and would nourish the Vibrio and thereby give rise to poisonous fumes that would poison the people. So his idea was to make the soil of Germany's cities infertile. And you could do that by depriving the soil of organic matter and excrement. So he wanted to supply Germany with clean water, but not specifically clean drinking water, but he wanted to prevent sewage from gaining access to the groundwater and the soil beneath the city. He also championed the idea of sand filtration of water to ensure clean water. He thought that snow had been seriously misled. There was a matter of proportion here. Snow, he said, was really concentrated on the few liters that a person consumed. That water, he argued, no matter how contaminated, would actually do no harm. The real issue was the massive quantity of water, of domestic, industrial, or household waste that carried fertilizer to the city soil and there bred disease. Now, Pettenkofer recognized then that clean water and effective sewage and waste disposal were essential public health measures. So he had, as his legacy, Pettenkofer was the founder of the sanitary movement in Germany. He was also professor of hygiene at the University of Munich. He founded a journal called the Archive for Hygiene in 1883, and indeed it's still published as the International Journal of Hygiene and Environmental Health. He was the founder of the Max von Pettenkofer Institute in Munich, a world-famous research institute dedicated to the promotion of public health. He became its director and trained people. It became a center of research and training unique at its time. He was an important figure in the founding of the Johns Hopkins School of Public Health. And along with his opponent, John Snow, he was a founding father in the field of epidemiology. His arguments, though now largely discredited, were supported by prodigious fieldwork. You can imagine him going around Europe, taking core samples of soil and rock, and correlating that with measurements of the rise and fall of groundwater levels, and correlating all of that information with rainfall, temperature measurements, and the history of cholera outbreaks. And Pettenkofer was tireless in propagating his ideas as a lecturer, as a writer. He was an advisor to the Bavarian government, and he became president of the Bavarian Academy of Science. Another factor was that Pettenkofer was quite interested in something else as well, what made people susceptible, and he believed that poor nutrition was an important factor in that. So his public health policies also involved attention to diet and nutrition. Of course, some of his recommendations were misguided, but one measure he gave great attention to was also the siting of infectious disease hospitals and cemeteries. A cholera hospital or a cemetery should be located on a hilltop, far from the city center and downwind of it. That would prevent the cholera germ from percolating down easily into the soil beneath the city, and would ensure that any poisonous miasma that arose would be dispersed from the population. So we can see that he helped the way Naples, for example, was rebuilt, and where the infectious diseases hospital in that city was located, which was high above the city and downwind from it. And as I said, to prove his theory, he tried his dangerous auto experiment. His theory was losing ground by 1892, when there was a major epidemic of cholera at Hamburg in Germany. And Pettenkofer and Robert Koch were greatly at odds. To prove his case, Pettenkofer challenged Koch to provide him with a cholera cocktail that he volunteered to swallow. Koch's collaborator, Gafke, duly dispatched a phial filled with Vibrios. There's some interesting ethical issues here, as Gafke sent Pettenkofer what he thought was a fatal dose of cholera, and fully expected Pettenkofer to die an agonizing death. There are then various accounts of what happened next. One account has it that Pettenkofer's lab assistants intercepted the package and diluted the dose. It's also true that the cholera cocktail was sent in February, and it may well be that the cold temperature in transit attenuated the virulence of the Vibrios. In any case, Pettenkofer was a man convinced of his theory. He put his life on the line to prove it, and he duly swallowed the phial that Koch's lab had provided. He fell seriously ill of diarrhea, but didn't develop the symptoms he recognized as Asiatic cholera. He rapidly recovered and was convinced that he'd proved that the Vibrio cholera does not directly cause the disease, not by being ingested. Well, there was an unhappy sequel for Pettenkofer. Koch's microbiology, by the 1890s, convinced the medical world of the germ theory, and miasmatic doctrine of all kinds, including Pettenkofer's own, were discredited. In 1894, he resigned his university chair. In 1899, he resigned from his other offices. In the 1890s also, 3 of his 5 children died, and his wife. And in February 9th, 1901, Pettenkofer committed suicide. Well, there's a final aspect I'd like to raise in my last minute, and that is to say, the defeat of Anticontagionism may have had some negative legacies that it took time to recognize. One of the strengths of Pettenkofer's ideas was the stress they put on what we would now call the environmental, social, and economic determinants of disease. For a time, the germ theory of disease relegated those aspects of medicine to the background, leading to a narrow-gauge stress on microbes and the attempt to find magic bullets to destroy them. So Pettenkofer, then, was ultimately wrong, but I would argue that his ideas were magnificently wrong, and that they contained important elements of truth and important and vital measures for public health and for medicine. Next time, we'll take the high road and move on to the victors in this debate, Pasteur, Koch, Lister, and the successful proof of the truth of contagionism in the germ theory of disease. But I thought you needed a moment with Max von.